My view is...
Okay, hello. This is the Math3611 and 5705 seminar. I'm William, and let's do some math. So for all of you guys in chat, it would be really nice if you guys could scan this QR code and sign the attendance form, just so that I can give us some money. We all like money, so that would be good. So here are all the chapters I'll be going through. I'm going to be going through sets and cardinality, and half of metric space. Christian is going to then take over for the second half, and he's going to do some metric space and some sequence and series functions. And lastly, on Gerald, on Friday, he's going to go through all the topological spaces and compactness. So just to begin, we're going to begin with some very basic definitions for sets and cardinalities. So we have that let n be natural numbers. A set S is said to be countable if either set is finite or the cardinality of S equal to the natural numbers, and uncountable if the cardinality of S is bigger than the natural numbers. Now, some example of the countable sets are the integers and the sets of rational numbers. So basically, you can think about it like this. If you could index them somehow, let's say put it in a sequence of x k's, if you could index them somehow, even though this sequence might be infinite, but as long as you could index the members of the sequence like x1, x2, x3, and so on by the natural numbers 1, 2, 3, then the set is countable. We have this nice proposition for union and Cartesian product of countable sets. Suppose I and S are countable sets, then the finite union of S are countable, and the finite Cartesian product of S is countable. This means that the Cartesian product and xn, which is something of the form like this, and you could replace any of these zeros with any integers, is countable. This also means that any natural numbers to the power of k, where k is a natural number, is also gives you a countable set. The countable union of countable sets is countable. So if A and S is countable, then the union of A and S is also countable. Next, we have some more definitions. Suppose we have set A and B, the following statements are equivalent. If there exists a bijection of A onto B, then the cardinality of B is less or equal to A. And if there exists an injection of B onto A, then we say the cardinality of B is less or equal to A as well. And note that if A equal to B, then there exists a bijection between two. So this is kind of fairly intuitive. So say if I have a set A and B, let's say for simplicity's sake, A has 3 elements. Let's say A has 4 elements and B has 3 elements. Then if we have a function of B going on to A, then we'll be basically mapping one, two, three, four, 1, 2, 3. Oh, A, B will be basically mapping 4 elements onto 3, and you can see there is a surjection, which implies that A is bigger than B. And similarly for the other way, if a function from B going onto A, So we have 3 elements going on to 4 elements. And you can clearly see that this is an injection. And if A and B, the size, oh, actually I had that, the size of A and B, not just A and B, the size of A and B are equal, then there is just a bijection. This is, again, another theorem. If A is less or the cardinality of A is less than equal to the size of the cardinality of B, and the cardinality of B is less than less or equal to the cardinality of A, then we have that the cardinality of A and B are equal. We'll be going through some questions. Oh, wait, I think okay. Well, the slides are supposed to be separated, so it doesn't show all the answers, but I guess that didn't. Okay, that I didn't explore it properly. Let's just go through some questions, I guess. So this is a 2020 question 1. So let S be the set of open disk in the complex plane, which have rational radius. Is the set countable or uncountable? So just gonna add a square paper after it. So this is basically, let me just write this here. Let S be the disk. Okay. So I just break the question down. So let S be the set of open disk in the complex plane. We just go through what open disk in the complex plane is. An open disk is the set B at point X epsilon. It's written like this, which basically means that all set of X in this is all set of Y in the complex plane, such that the distance between X and Y is less than epsilon. That's what an open disk is. And this question might seem really complicated at first, but we can kind of break it down. So instead of thinking about the rational radius first, we can just look at how many open disks are there possible in the complex plane. So we know that in a complex plane, any element of the complex plane, let's say Z of the complex plane, is of the form Z equal to A plus BI. And we might not know if this is countable or not, but we can kind of break this down into we can kind of find a function that takes the complex numbers into the Cartesian product of I can't write it in of Cartesian of two natural numbers. So we have that we can send A plus BI into A and B. And we see that this obviously will give us a bijection because we are sending this to this, and A could be anything, sorry, this won't give us bijection. This would give us, so that should be R times R, and this will give us a bijection because A can be any real number, and B goes to B, and B could also be any real numbers. So we know that the cardinality of C equal the cardinality of R times R. But from before, we also know that the Cartesian product of countable sets give us countable sets. But we know that R is uncountable because R is bigger than the cardinality of the natural numbers, right? So we have that this is uncountable, and this is also uncountable, right? So we have that. Now, what can we do with this information? So let's say we have like a Cartesian grid over just a R by R grid over here. If there are uncountable amount of elements in the on the grid, it doesn't really matter like if the radius of the circle is like 1 or if the radius of the circle was like a quotient number. So we have like, so let's just simplify this question and say the radius of the circles were not a rational number, but the radius of the circle was all equal to 1. Then we can still form at each of these points, we can still form a circle regardless. And since these points are uncountable, then it kind of just follows that the circles with radius 1 are also countable. So then that also implies that any open ball with rational radius is also uncountable. So just, yeah. So that's pretty much the logic behind this question. Next up, we have 2022, question 1. We want to determine whether the following sets are countable or uncountable. So we have the sets of rational numbers. We have obvious listing. This is countable. We have the sets of bit strings from that's of the form of B1, B2, B3, and so on, where BI is either 0 or 1. We have the set of the Clopin sets with of R with the usual topology, and we have sets of Clopin sets with R with discrete topology. So let's make a page after this. So I mean, you can see this is, or it says it's uncountable, but we'll just go through why. So part B, the sets of bit strings is uncountable because we can consider the power set of n. So the power set of n is basically sets of the form A, B, A, B. So basically it's all possible sets of n, and from Cantor's diagonalization theorem, we know that n does not equal to the power set of n, right? So now so to think about the bit strings of 0 and 1s and so on, we can kind of think about them as if a specific element of the power set. So we have, if I have the bit string 1, 0, 0, 0, 0, all zeros, then we can kind of think about this is the power set of 1. If we have the set, the bit strings 1, 1, 1, 0, 0, 0, 0, and so on, we can think about this is as a subset of the power set as 1 dot 2 dot 3, and so on. And we have another example, 1, 0, 0, 1, 0, 0, 0, and all zeros, so on. This is then can be mapped to the element 1, 0, 0, so 2, 0, 3, 0, 4. Right? So we can kind of map it like this. And so we see that there is a bijection between the power sets and the bit strings infinite length. So we also know from class that the power set of n is uncountable, so it then follows that the bit strings are also uncountable. The sets of clopin sets of R with usual topology. R is just a straight line, so what they say by usual topology, and by definition, the any clopin sets that are both open and closed is just R and the empty set itself. So since there's only two, it's obviously countable. Next, we have the set of clopin set with discrete topology. So this will come up later, but just to give you guys a definition of what discrete topology is, basically is suppose we have element S. The discrete topology on S is if we have A and B from S, if A equal to B, if A equal to B, then we say if I have the how to write this? If we have the space A equal to B, then we say this is open. And if you have to say if A doesn't equal to B, then we say the space is closed. So if we have R with the discrete topology, then this basically means if we have, let's say, so if we have R and we have, say, 1, then if 1 equal to 1, all right, that gives us the open set. And then if 1, and obviously 1 doesn't equal to for any, like, if I have 1 and we have any x in R, if 1 equal to x, which x has to be equal to 1, then we say this is open. And if x is anything else that's not equal to 1, then we say it's closed. And so obviously then every element of R is just open by itself. So 2 is open by itself, 3 is open by itself, 4 is open by itself, 5 is open by itself, and so on, right? So every element of R is open. But we also know that from definition that a set is closed if its complement is open, or we can say a set is open if its complement is closed. So obviously we have if 2 is open, the singleton of set 2 is open, and then obviously R minus R getting rid of 2 will also be open. Will this by definition, since 2 is open, the set, if we get rid of R, this set should be closed, right? But we know that if the set get rid of R, it's just the singleton sets of, it's just a set of 1, 3, 5, 6.5, so on, just a real number without R. But each of these singleton sets, let's call it X, they also give us an open set. And we have that any union of open sets is also open. So R without the singleton set of 2 is also open. Right? But if we take the complement of the set again, so R complement, well, if this is open, then if we take the complement of this, complement, this should just give us back the singleton set 2. But we know the set is open, so therefore the set is both open and closed. So we have that so then this is clopin. So we then have that every element of the of the real numbers is both open and closed at the same time under the discrete topology. Next up, we have this quite interesting question. So, is the set of functions from Q to Q countable or uncountable? So the rationals. So now we can first note that the Q itself is countable because the cardinality of n equals to the cardinality of Q. So instead of looking at the set of functions from Q to Q, we can look at the set of functions from n to m to simplify things a little bit. Now we also note that the set 0 to 1, 0, 1 is in the natural numbers, and so we can look at the set of functions to make things even simpler. We can load at the set of functions from n to, this should be from n to 0, 1 instead, because since this is a subset of n, it inherits all the probability of n, so we can look at that instead of looking from n to n. Now suppose that the set of function s is countable, so the set of function s is the set of function from s to 0 and 1 is countable. And further, suppose that each of the functions fi, where fi is in S, we have this each of fi's, and we can write bi's like this. We can write bi is fi map to 0, so, and then fi1, fi2, and so on. And so each of the fi's ends are either zeros and ones. So this is 0 or 1, this is 0 or 1, 1, and then this is 0 or 1, and so on. And so we can construct B now. We can construct a B with B0 and B1 and B2, where BI's is, I guess, the inverse of each each specific position. Say if you have B1 equal to 1, 0, 2, 3, 4, 1, 1, 1, 0, 1, 0, 1, so on, and B2 equal to 0, 0, 1, 2, why am I writing 2? 0, 1, 1, 0, and B3 equals to 0, 1, 0, 0, 0, 1, and so B4 equal to 1, 0, 0, 1, 0, 0, 1, and so on, and B5 equal to 1, 1, 1, 1, 1, 1, 1, so on. Let's just do 5 examples. And then so B here will be, look at B11, so this is this number here. It will be 1 minus that number, so we have 0, and we look to B22, that's 0, so this will be 1. We look at B33, that will be 0, so it will be a 1 here. We look at B4 F44, that will be 1 again, and then we look at B5, and since there's a 1 here, this will be a 0 here, and so on. And we do this over and over again, and we can see that this B doesn't equal to BI because it differs in the first position. We also can see that this B doesn't equal to B2 because it differs in the second position, at least in the second position. And then we can see that B doesn't equal to B3 because it differs in the third position, at least in the third position, and so on. And we can see that we have created an element B that is not in the set S. That is not in the set S. But we have assumed that S is countable to be a set of function countables. Now, from this B, we can then construct a function where construct a function f, where f of 1 goes to 0, f of 2 goes to, sorry, starts at 0, f of 0 goes to 0, f of 1 goes to 1, f of 2 goes to 1, f of 3 goes to 0, and goes to 1, f of 4 goes to 0, and so f of b I should write that there. So f of, let's just, okay, I'll write it in red so it distincts from all the other bi's. F of b I goes to either 0 and 1. And we can see that this f here doesn't equal to any of these f's there, because it maps to a different element on at least the ith position, the ith position. So we have constructed an element that's not in the set S, but we have assumed, since I've assumed that the set S is countable, this kind of breaks our argument. So we must have that the set of S is uncountable. Right? So then, yeah, since B, so there is this, so then it follows that there is this uncountable amount of functions from n to 0, 1, which follows that there is an uncountable amount of functions from n to n, and so on, and it follows that there exists an uncountable amount of functions from the rationals to the rationals. Next up, we have metric space. Okay, some more definitions. Let X be a null-empty set, a function D, where it takes the Cartesian product of X and X to 0 infinity, including 0, is a metric space if it follows to satisfy the following conditions. If the distance, I mean, if you think about this, you can think about it as like distance. D kind of, the way I kind of think of a metric space, I kind of just think about D as a distance between 2 points on a given set, though like sometimes those distance might not be linear. Just example is just R with your usual metric space, which is X minus Y for X, Y in R. And you can see that this kind of satisfies this property because this absolute value equal to 0 if and only if X equals to Y, else this absolute value is also greater or equal to 0. And symmetry, so basically using this example again, this is just X minus Y is equal to Y minus X, and triangle inequality, which is X minus Y is less or equal to X minus Z plus Z minus Y. That might not look like your usual form of triangle inequality, which is A plus B equal to less or equal to a absolute value of A plus absolute value of B, but we can kind of like change this around to look like that. Some more example of metric space are R with the usual metric, as I mentioned before. Any non-empty function, and if X is a non-empty set, then with the function dx of nx to 0 and 1, this gives us discrete metrics. It's kind of like the discrete topology. It's like almost like exactly the same as the discrete topology we talked about. It maps to 0, if x equal to 0, x equal to x, or if x equals to y, and it maps to 1 if x doesn't equal to y. Now we have an interesting one called the river topology. So we define this function over here, right? Find this function over here. But so basically, okay, it's kind of hard to explain in words. I'll just draw it out. So we have this, say we have this Cartesian plane. We can think about the this y as a river, and these are kind of like, or like a mountain or whatever you call it. This is we'll call y a river, and the rest are mountains. If say we have the example where y equal to y to 5, and this is 2, 3, right? And the distance between these two would just be that, which is 2. Now, if we have the second case where x dash does not equal to x, say we have something like this. I'll use a different color. Two. No, negative 2 and 3. And we have the point 2 and 3. I mean, they're not exactly to scale, but it will show the point. So if you have that, if that's the case, then we kind of, what we do is we need to travel, kind of like travel downwards and then cross from this distance over here and then go upwards. So it's kind of like if you're like, say this is like the set of mountains over here. If you're not on the same side of the mountains, you gotta go walk along this river, which is our x coordinate, and then go upwards to travel to our destination. And that's kind of the idea behind this river matrix, and it's pretty interesting. Okay, next we have more definitions. Convergence on metric space. Let x and d be a metric space. X equipped with d be a metric space, and suppose that xk is a sequence of element of x, and suppose that x is in x, then we say x of k, xk, the sequence xk converge to x in matrix D if the distance between xk and x goes towards 0 as k goes towards infinity. Alternate delta epsilon definition is xk goes towards x as k goes towards infinity in the metric space. If for all epsilon bigger than 0, there exists k such that for all k bigger than big K, xk, the distance between xk and x is less than epsilon. Then we also have that the limits in the metric space are unique. So this is saying if xk goes towards x and xk goes towards y, then x and y must be equal. Now next we have topology on metric space. But basically topology basically means the set of open sets on the metric space. And this will be covered more in details by Gerald on Friday. Suppose we have the metric space x equal with d, and y is a subset of x. X is 0 is called an interior point if there exists an epsilon such that the open ball bx0 delta is completely in the subspace y, the subset y. So say we have, this is our x and we have our y here. Now this will be interior point because we can draw an absent ball around it, such that this point x0 is completely contained in y. Now an x0 is called a boundary point for y. Of y, if for all epsilon the open ball intersects the y is not empty, and the open ball intersects x complement y, x minus y is also not empty. So basically what it means is that this is the x1, let's say x1 is a boundary point. If no matter how small of an epsilon you get, you always contain elements both inside of y and outside of y. So it doesn't matter how small you shrink this ball, you'll always contain elements in y and outside of y. Now open and closed. Y is open if it contains only interior points, and y is closed if it contains all of its boundary points, or if x minus y is open. Now continuity at a point, let x equivalent with dx and y equivalent with dy be a metric space, and suppose that f maps from x to y, then f is continuous at point x if for all epsilon bigger than 0 there exists delta bigger than 0, such that the distance, the dx of x and x0 is less than delta, then we have that dy, the distance between f of x and f of x0 is less than delta. So that's just a lot of words, but if we have x and y here, to make sense of this more, and we have these two sets, so we have a point x like that, and this is f of x here like this, and say this is, we have a delta ball like this, not a very nice ball. Then if we pick any points, and then we have an absent ball like this, that's saying if I have any point x0 inside of this delta ball, it will be mapped into some point in the epsilon ball of f of x. So no matter how small the delta ball gets, if it shrinks down and we pick an x in like over here, x0 over here, then this will map to a point closer to a small delta of f of x0. That looks a bit more like a mess, but I think you guys will get the point. The preimage theorem, let x and x equip with dx and let y equip with dy be metric space. And suppose that there's a function going from x to y, then f is continuous on x if and only if the preimage of any open sets is open for all open sets. So again, with this ball example, x, y, if we have a open set u, U, it looks like a W, u over here, then if we take the preimage of that, this will give us an open set, and then we say that f is continuous. Next up, bounded and compactness. Suppose we have a metric space, that should be brackets, and y is a subset of x. We say that y is bounded if there exists an x in existing x0 and m in R such that for all y and y, the distance between y and x0 is less than m. If y is both closed and bounded, then y is compact. A really basic example is just say we have the set x over here and we have y, then if y was like this, say this is a ball of radius epsilon, then we can see that this ball is clearly bounded, and if this ball contains all of its boundary points, then now this ball is not closed, and we say that this ball is closed and bounded, so it's compact. Interesting thing about compactness is that compactness is preserved under continuity. So if a function f is continuous, and we want to map this somewhere here into the set y and w, then it will, this f of, let's call it u, this f of u has to map to a compact set. So the image of a compact set is also compact under a continuous function. Next up, we have some questions. So let R be a function, let f be a function defined from R to R, and define f of x to be a piecewise function. If x is bigger than 1, we have that 2 plus 1 over x. And then if x is less or equal to 1, we have that f of x is 1 plus x. Now I want to show that d given by dx and y of y is given by the absolute value of f of x minus f of y, and give us a metric on R. And want to find the open ball of 2 with radius 1 over 2 on this matrix, and want to find the closure of the interval of 2 and infinity on this matrix. So we'll start with part 1 first. Now, part 1, by checking that, there's a few things we need to check. We need to check that 1, that dx and y greater than 0, and dx and y equal to 0 if x equal to y. I'm going to check that 2 dx and y equal to dy and x. And lastly, you want to check the triangle inequality. 1 and 2 is pretty simple to check, so I'll leave you to check that at home. But we'll just check for the triangle inequality over here. Check for the inequality over here. So suppose we have dx and y like that. And then we have f of x minus f of y. And we know that we can apply a triangle inequality on this. So this is less than f of x minus f of z plus f of z minus f of y. And so applying triangle inequality to this, we get that this is less than or equal to than f of x minus f of z absolute valued plus f of z minus f of y absolute valued. And this obviously gives us dx of z plus dz and y. And that gives us what we want. right? So that shows that this D over here defines a metric on R. Now, what about the open ball centered at 2 with radius 1.5? So, like, if it's on R, right, you would inclined to think that the open ball centered at 2 with radius 1/2 is something that looks like this, right? But that won't be the case here because we don't have the usual matrix. We have something like kind of weird. So we'll go through and find this by definition. So first, we will go through what an open ball again is again by definition. So an open ball centered at 2 with radius 1/2 by definition is the set of points in R such that the distance between x and 2 is less than 1/2, right? But this distance here is not our usual distance. And this distance here, if we have distance of x and 2 is less than 1/2, then we have that f of x minus f of 2 is less than 1/2 by our definition of our metrics, of our function, sorry. And we see that 2 is bigger than 1, so we have that this equals to f of x minus 2.5 less than 1/2. So this is equal to f of x minus 2.5 less than 1/2 and negative 1/2. And this is equal to -2. Sorry, this is equal to 2. F of x is sandwiched between 2 and 3. So now we want to find all suitable x that suits this criteria. So we go up and look at how our function is defined again. So we see that if x is less than 1, we have that 1 plus 2, we have the function 1 plus x. If x is bigger than 1, we have the function 2 plus 1 over x. Now, as you've noticed here, as x tends towards infinity, this part is upper bounded by 3. So there's an upper bound of 3. Oh, sorry, as x goes towards infinity, this approaches 0, so we just end up with 2. And as x goes towards 1, this gets closer and closer to 1. This part here goes closer to 1 as x goes to 1. So 3, right? So we get this gives us nicely the interval we're looking for between 2 and 3. So the set of open ball from 2 with radius 1/2 is actually the interval from 1 to infinity, not including 1. Next up, we have question 3. We want to find the closure of y. We want to find all written CLY, where y is from 2 to infinity. So basically it means that we want to find the set that includes y and all the boundary points of y. Y is just this. Now we just got to find all its boundary points of y, or limit point. One way of doing this is just by looking at what happens to y as each of these sets goes towards infinity, right? So we can look at endpoints and suppose that we have a sequence of f of xk in y. Now as xk, and that's such that xk goes towards infinity as k goes towards infinity, then clearly we see that f of xk goes towards 2, because the sequence f of xk equal to 2 plus 1 over xk, and as k goes towards infinity, this part goes towards 0, so that just gives us 2. Right? Now we notice that the distance between xk and this 1 here also tends towards 0, so this is the xk and 1, which gives us the absolute value of f of xk as k goes towards infinity, and f of 1, we see that if x is less or equal to 1, we have the function of 1 plus x. So this goes towards 0, and we have that our sequence xk, k equal to 1, goes towards 1. And so 1 is a boundary point, or a limit point for our set y. Next, we can look at what happens if we have a sequence of yk in y, and that should be y of k goes towards 2 as k goes towards infinity. Clearly, we see that f of yk goes towards 2.5, because if we have the function f of x, let's turn it up again. So we have a function over here. If our x goes towards 2, right? This goes to 2.5. And so we also notice that the distance between, if we take, that's just the same as equal to f of 2, because f of yk minus f of 2, this gives us 2.5 minus 2.5, and that goes towards 0. So we now have that 2 is also a limit point for our set y. So since we looked at already boundary points, the two possible approaching points, they can't possibly be any other limit points. So we have that the closure of y is equal to 1 union to infinity. That. Next up, we have another question. So want to show that given a point x, the function dx defined by the usual metrics, so d of x y equal to the distance between x and y is continuous. I want to show that if y is a non-empty compact subset of x, then each of the following point x and x, there's a closest point to x and y, i.e. a point in y such that the distance of x and y is less than the distance of x and all otherwise. To do the first part, one show is continuous, and so we can do this by definition. Now recall from earlier, the definition is that if we want to show dx to r is continuous, we want to show that for y and y dash in x, then if y dash is less than delta, then dxy and minus dx y dash is less than epsilon for all epsilon bigger than 0. So that's our definition for continuity on the metric space. So we'll just begin to look at this part first. So suppose we have dx of y minus dx of y dash, right? Then this, by definition of our d of x, this gives us x minus y minus x minus y dash, right? And by the inverse triangle inequality, which is that if we have if we have a minus b, then this is less or equal to than a minus b. And so this is less or equal to x minus y minus x minus y. The x cancels out, so that should be a plus there, so we have y dash minus y. Now this is less than epsilon, so if we set our delta equal to epsilon, then we have that this condition of household, and so d of x is continuous. Yep. Now for part 2, we want to show that y is a non-empty compact set of x, then for each of point x and x, there is a closest point to x and y, such that the point y the distance between x and y is less than all distance of x and all otherwise. So to draw like a picture to make this easier to understand, so we've ever set x and we have a compact subset of y like this, which is, I guess you can think about it as like a closed open ball circle. So what's saying that if given a point x over here, there exists a point on y such as this point, so that the distance between x and y is less than all distance from all otherwise in this compact set of y. Now this doesn't seem very intuitive at first, but given that we have proved part 1, it kind of hints to us that it wants us to use part 1, and also because the distance of x and y can be defined by a function of the x and y, which is continuous. So now we use the fact that our function here from part 1 is continuous. So suppose now, since y is compact and we have our function dx of y is continuous, so then it follows that dx of y is also continuous, since big Y is a subset of x. And from earlier we mentioned that compactness is very nice because it gets preserved under continuity, right? So what it means is that this set here is also compact, right? And now since this set is compact, then therefore it is bounded, right? And closed. And if it's both bounded and closed, then there exists a minimum value. There will exist a minimum value such that there exists some y in y such that this is the minimum of the x y, right? And that kind of is what the like the basis of our proof is. So it goes that since it's continuous, then y is compact. Then it follows that the x of y is also compact, right? So there is this a y dash such that dx of y dash is the minimum of the x and y, and so therefore that we have that the distance between this x and y dash is less than the distance of x and y for all y in y. Just before I finish up, I'm going to go through some definitions for norm space and examples before I hand over to question. So a norm space, let V be a real vector space in function, be a function, then we say that function is a norm if it's satisfying the following qualities. If it's linear, if we can pull given any real numbers, if we can pull it out. If it's like absolute value, I guess. Another way to think about this is the norm of V is always bigger or equal to 0, and norm of V is equal to 0 if and only if V equal to 0, and we have triangle inequality gets satisfied. Now this is but this is also a norm on vector space V. Then setting the function to be dv of u is norm u minus norm V. This will give us a metric space on V. And here's some example of norms. We have the L1 norm, which is the set of all summable sequence. We have the supreme norm on the continuous function from 0 to 1, and we have the 2 norm on the continuous functions from 0 to 1. Inner product space, let V be a real vector space, then the inner product space is a map such that it follows the following quality again. The inner product of V on itself is bigger than 0, or equal to 0, and equal to 0 if V equal to 0. It is linear, so we can pull lambda out on the first place. And it is symmetrical, so the inner product of a V and U is the same as the inner product of U and V. And it's associative, I guess. So inner product of U plus V with W is the same as inner product of U and V plus the inner product of V and W. Now, this doesn't have to be applied to the real vector space. This could also be applied to the compact vector space. Some examples are Rn and Cn with dot product, and the set of continuous functions over 0 and 1 with inner product defined by this. This doesn't have to be 0 and 1. This could be any continuous bounded interval, like A and B. Switch that out to be in general. And that will be it from me. Alright, I'll hand you guys over to question, and you guys will do some more metric space and followed by sequences.
Okay. We will just wait for this to pop up, just to make sure that everything's going all right. Alright, here we go. Hello everyone, my name's Christian. Thank you very much, Will, for that presentation. Very good. So, just before we get into the rest of metric spaces, just if you haven't had the opportunity yet, if you could sign this QR code, we would much appreciate it. I'll just give people a second to just grab their phones and scan that if possible, but we'll get into things in a few seconds. Okay. So page 63, there we go. So we just got to finish off metric spaces. So we'll just talk a bit about first completeness. To discuss completeness, we'll first remind ourselves of what a Cauchy sequence is. So we say that a sequence is Cauchy in a metric space xd if for every epsilon, for every tolerance, there's a k such that at every point past that k, the distance or the metric applied to any 2 points is less than epsilon. So if you have a set x1, x2, x3, x4, let's imagine that we said we had an epsilon that we had chosen that gave us a k of, let's say, 3. So k of our epsilon is equal to 3. Then what we'd say here is that any of these elements, x4, x5, x6, x7, and anything in the dot, 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 their distance, d of, say, x4 and x17, is less than epsilon. And that holds for any pair you choose in this green section or beyond. Okay. So a nice result is that every single sequence that is convergent is also Cauchy, but it doesn't necessarily go the other way. We say that a metric space is complete if it does go the other way, if every Cauchy sequence does converge. Wait, no, sorry. What is it? Yes, every Cauchy sequence does converge. Okay, cool. Then just as an aside, Hilbert spaces and Banach spaces. A Hilbert space is a complete inner product space, and a Banach space is a complete normative vector space. I couldn't find really questions to do with Hilbert spaces or Banach spaces, but we will be seeing Cauchy in a second, I believe. We've then got contraction mappings. So a contraction mapping is a function from a metric space to itself that satisfies this idea. So the distance between the function applied to any 2 values in the metric space, in the set of the metric space, is less than or equal to the distance or the metric applied onto the 2 points themselves. With little constant c here, c has to be between 0 inclusive and 1 exclusive. That brings us nicely to the contraction mapping theorem, where if we have a contraction, then we know that there has to exist some unique fixed point xf such that fxf equals xf. Very helpful for ODEs. There's a section in the notes on that. I didn't include a question on that, but the techniques we're going to be using for this question coming up are very similar to what you'd use just regularly for if f was a differential operator, if it was an integral or a derivative of some sort. So let's take this question from the 2016 exam, question 3b. 3a was basically just stating the definition of a contraction mapping or the contraction mapping theorem. I've forgotten a little. So we'll say here, let xd be a metric with the set 1 to infinity, 1 inclusive, infinity non-inclusive, with the regular distance metric, just the absolute value difference. Let's define a function by this, x plus 1 x. We have to first show that the distance between the function values is less than the distance of the actual values for all x not equal y. Then we've got to comment on whether it's a complete metric space, so whether all Cauchy sequences converge, and finally discuss fixed points and the contraction mapping theorem. For part I, I'm going to be using this quite a bit. I just use this little kind of condensed notation. It's just we've got the sets and we've got the actual mapping. I should have written that as x maps too, but that's okay. All right, so the first thing we're going to do, we're just going to take x is not equal y. By the symmetry of the absolute values and the distance metric that we're dealing with here, we are just going to fix x greater than y, and we're not going to lose any kind of generality. You can just apply the same arguments we're going to be applying with y greater than x. So we take just the difference of the function values, take that. You can factorize it a little bit, just factor out x minus y, get 1, factor it out of here, you get minus 1 on xy. And a nice little thing is that since x is greater than y, and y is greater than or equal to 1, this gives us that multiplying the two values together, well, we have a number greater than or equal to 1, and we have a number greater than 1. So the result is going to be greater than 1, giving that 1 on the result is less than 1. But we also know it's greater than 0. And that allows us to state, oh, well, this little figure here is kind of what we want. It's going to allow for this inequality to happen. Okay. So, and that has demonstrated exactly what we want. Is it a complete metric space? So what we'll say here is we'll look at a little proposition here, proposition 2.10.12. For a complete metric space, a subset of that set paired with the same distance metric is a complete metric if and only if y is closed in x. We're going to use the fact here that 1 infinity is a subset of the reals. And then comment on the completeness of the reals with the regular distance metric. So what we can say here is, yeah, this is closed. Now, not sure of what's gone on. Oh, I know what happened. Okay, yes. This is going to happen quite a bit. That's meant to say R. I had, oh no, that's okay. In my slides it should be fine. It's just going to be for these few slides. But that should be say R, and this should say R as well. I just haven't put the command in the LaTeX document. So yes, we've got to complete metric space, and we're good. Now talking about whether f has a fixed point, we're showing that it doesn't. Let's consider the problem. That gives 1 on x equals 0, which has no solution. No solution in x between 1 and infinity. This doesn't quite violate the contraction mapping theorem, just because there's no c in 0 to 1 such that this holds. It's not a contraction. And so the contraction mapping theorem does not apply, and the fact that this doesn't have a fixed point doesn't violate the contraction mapping theorem. Okay, so now we can get on to series and sequences of functions. Before we do, I'll just check if there's anything in chat. If anyone's let me know that I am not able to be heard. Looking good. I'll come back to that in a moment, but here we go. Okay. Sequences and series of functions. So let's remind ourselves of a few definitions. We'll get to a lot of questions as we go on, but it's going to be a lot of definitions as well. For a set, we'll take k being an element of the set of natural numbers, and we'll define fk for the positive natural numbers, maps a to r, and we'll take some function mapping a to r. We'll say that the sequence, this notation is used a lot. We say the sequence of singular fk as shorthand for the sequence fk running along appropriate values of k. In our situation, that's k in the positive integers, or k runs from 1 to infinity. That is used a lot throughout this presentation, so when you see that, it means that. We say that it converges pointwise to f if for all a and a, fka approaches fa in R as k approaches infinity. So an example of that is, let's take the sequence of functions fk of t equals arctan kt. This takes on a few different sections. So you've got, let's go to page. You have here the situation where first f, no, that's white. So x being less than 0 gives us that fk of, we'll do greater than 0 first. Fk of t, we should do t greater than 0. Well, that's equal to arctan kt. T greater than 0 means that as k approaches infinity, this entire term is going to approach infinity. So k approaches infinity implies kt approaches infinity in our situation here. Or that fk is going to approach, well, as this approaches infinity, you're going to get pi on 2. Just a little arctan thing. Very similar thing with a negative. We can say that this is equivalent to saying t equals negative capital T, where t is greater than 0. So this gives us that fk t equals negative arctan k capital T. Because of the oddness of arctan, we're able to take the negative out. And through the same kind of logic up here, we get that approaches negative pi on 2. And then finally, I'll just separate you. We'll say here t equals 0 gives fk is arctan 0, which is just 0. So no matter where t approaches, no matter where k approaches, we get that's going to always stay 0. So we get this kind of piecewise definition. Now, something that, yes, something that I forgot to comment on down here was that we are actually dealing with the closed bounded interval -1 to 1. So you would just change this to less than or equal to 1, and that's greater than or equal to, what is that? Yeah, -1 over there. Okay, so next we have pointwise convergence generalized for metric spaces. I don't know that we went through an example of this previously, but we say that for a metric space, same function ideas, just instead of mapping to R now, we're mapping to X. Okay, same idea with F as well. We say that the sequence converges pointwise to F in the metric space XD if, for all A and A, FKA approaches F of A in the metric D. A lot of similar stuff, you're just being a bit more overt and taking more into consideration the metric you're using when you're talking about something approaching 0. Okay, so let me just check that. Yep, that's all good. So yeah, we won't cover this in depth, cover the metric spaces. Uniform convergence is then when we have A, a set, and BA being the set of all bounded functions with domain A. A sequence of functions, fk in BA and f in BA. We say that fk converges uniformly to just f if it converges to f in the d infinity metric, that is this. So d infinity, the distance between them, which is this notation, approaches 0. We do have an example that uses pointwise and uniform convergence, so let's have a look at this. For k, positive integer, define fk mapping 0 to 1 to r by this piecewise function. So 1 when x is 0 and sine kx on kx between 0 and 1. So we'll look at pointwise first. The thing you usually do when you're talking about pointwise and uniform convergence is, I'm not sure if I commented on this anywhere, but uniform convergence implies pointwise convergence. So I might add that up here. uniform implies pointwise. And uniform is kind of informed by pointwise as well. They should have the same limiting function. So the pointwise is often the easy one to find, so we find that first and then just check, does our function converge uniformly to that pointwise function? So we'll just use a little few facts here. So obviously the pointwise limit function f should have f of 0 equals 1. This isn't going to change, so we'll just fix that. And then let's consider x between 0 and 1. So since sine t is between -1 and 1, a careful pinching argument gives this. So the pinching argument we'd be looking at here is to do with, we have -1 less than or equal to sine t less than or equal to 1 for all t. So we can sub in t is kx. We can then divide by kx. This is the careful bit because we've assumed x is non-zero. So it's not too careful, but you still have to kind of comment on it or worry about it. We've also assumed that it's positive and that kx is positive because k is greater than or equal to 1 and x is greater than 0. So we don't have to worry about any kind of flipping of inequalities. And yeah, pinching theorem, we can see since x is greater than 0, if you take the supremum of both sides here and here, the limiting supremum, then you'd get that this approaches 0. And so we can define our pointwise and piecewise function. So it's 1 for x equals 0 and 0 otherwise. Now that we've gone through pointwise convergence, we'll talk about uniform. So if we have a function converging uniformly, then its limit is continuous. Taking the contrapositive of the result here gives that if a limiting function is discontinuous, or the potential and only possible limiting function is discontinuous, then we don't have uniform convergence. So we get that since our function is discontinuous, it converges, well, pointwise, not uniformly. Okay, so let's just have a quick look here. No, nothing in chat. We're all good. Okay, so the Weierstrass M-test. This is where we're getting onto series of functions and the convergence, uniform and otherwise, of them. So let's take a sequence of functions in CBX. So this is the set of continuous bounded functions with domain X. And that there's a sequence of constants, mk, so matching fk to mk, such that the infinity norm of fk is less than or equal to mk. So that's how mk is defined for each fk. And that's all for positive integers k. If the sum of that sequence of constants, the series, converges, then the series of the functions converge uniformly to some function. Doesn't necessarily tell us much about the function, it just tells us that there is one. So this is the kind of more generalized version. There is a Weierstrass M-test 1 and a Weierstrass M-test 2, but I believe that this also covers the M-test 1. Now, to use the Weierstrass M-test and to find these constants m and whether they converge as a sum, it helps to look at these ideas of convergence of sequences and, well, no, convergence of series. We say that this series doesn't really matter the sum, just taking an infinite sum, converges if the lim sup of the ratio of the next term of the previous term less than 1, or lim sup of the kth root of the absolute of the kth value is less than 1. That's the ratio test and the root test together. We will do an example using both of them. I believe that's this one. So what we've got here, define, just check Counting the time, no, all good. Define fk mapping 0 to 1 to r by this function. We have to prove that this series converges uniformly to a continuous function on 0 to 1, so perfect for the Weierstrass M test. What we'll do here, let's construct our sequence mk. So we know we want this to be satisfied by all mk. So we'll start with that, expanding the definition of the infinity norm as the supremum on the domain of the absolute value of the function. So what we can do here is just work on that supremum a little bit, but what do we say here? Since fk is continuous and positive on 0 to 1, it suffices to consider local maximums via derivatives and boundary points. So yeah, continuous, only turning points, and only only maximums are going to be either at the boundaries of 0, 1, or at local minimums and maximums turning points. Differentiating gives us a maximum at t equals 1. You can do this by hand via maple. You'll get t equals 1, which is already a boundary point, so we only really need to test 2 points. We'll test f0, gives 0. f1 gives kek to the -1. So we'll take that value since it's the greatest of all of the maximums that we found. Okay, and we're allowed to take just that value because it's a greater than or equal to. So we can pick equals to, and this should be the minimal for each. So since we found that mk, then we can say that st converges if this converges, if the sum of mk converges. We'll do the ratio test, so take the after term over the previous term, work on simplifying a bit, and we can then take the limiting supremum. So we can see here that the lim sup this term is going to be less than or equal to 1 on e because the lim sup, well, 1 on e isn't going to change the lim sup, but k on k plus 1 has a limiting supremum of 1. And so we can see here, doesn't matter whether this is a less than or equals to, we just care about the fact that we get 1 on e, which is less than 1. So the series of mk converges, and we get a sequence, a function the sequence converges to. The series, my apologies. Okay. We'll do it again, just that same step, but we'll do it with the root test. The root test is a bit more careful in this case, but I wanted to find a case where we could use it. So what we can do here, kth root of the absolute value doesn't matter. This is already positive. And just applying some index laws, we get this little thing. So we can say here that the limiting supremum of that is 1 over e, even -1, times the limiting supremum of x in the positive reals of x1 and x. Now this is a step worth explaining. So we've got here that this is really defined for k being positive integer values. Now the positive integers are, of course, let's go here, a subset of the positive reals. And so if we find a kind of supremum on the reals, the positive reals, then it's going to be an upper bound for the supremum on the integers, on positive integers. So we can just find a supremum in the positive reals, and I saw that this would be nicer to do because this is a continuous function for the positive reals. And we'll get to the supremum through differentiation, is just e to the -1 on e. Yeah, that is right. I made a typo in that earlier, I'm just making sure it is correct. And we can see, yeah, that's less than 1. So we're good. So we get that the series mk converges by the ratio test, and again, the series S converges uniformly to some continuous function on 0 to 1. Okay. So let's just check the chat. Yep, everything's all good. Right, so now we'll talk a bit about differentiating and integrating limits of sequences. So sometimes we want to question when we can interchange limits and derivatives or integrals. So we say that we can kind of interchange the derivatives and the limits when if all of a sequence fk, this is the sequence, continuous functions on 0 to 1, this is actually a non-equal to because uncountable, countable. So we say that if all of the fk are differentiable on 0 to 1, if we say that fk approaches f uniformly, we say that f dash k is a continuous and bounded function on 0 to 1. That is the non-inclusive. This is inclusive here. And we have fk dash approaches some, I always get phi and psi mixed up, some phi uniformly. If all those conditions hold, then f is differentiable on 0 to 1, and f dash is equal to phi. If then, with limits and integration, the sequence fk converges uniformly, then we can say that on this kind of bounded integral, on these bounds that are not, what was the term? I've forgotten. None of them are infinite, is pretty much the idea. Then we say that we get this approaching this. That breaks down sometimes when you have infinite integrals, but at least for 0 to 1, and by extension, just any kind of finite, any bounded closed interval, and then you're good. And I think even non-closed. We'll talk a bit about differentiating power series. So if you have a power series here, and you say that it converges pointwise on the disk, the open disk of R, radius R, around 0, disk, then we say that S is differentiable, this series is differentiable on that disk, 0, where the derivative is just the term-wise derivative. You just differentiate each term. Of course, this starts at 0, this starts at 1. That's because the constant term at the beginning, the z to the 0 term, disappears. Okay. These topics don't come up too much on their own in exams. They usually like to aid proofs of other kind of results and theorems, or at least used as a small part of other larger problems. Here we'll focus on convergence of series, just because it's such a common type of exam question. Shows up about once every year, and it's kind of worth going through. So I found this interesting problem from the 2021 exam. If we consider the sequence of, actually before we get into it, let me just, nothing in the chat, cool. So let's consider the sequence of piecewise linear functions, fn from 1 to infinity, continuous on 0 to 1, where fn is 0 outside of this interval, and it has a symmetric spike of height 1 on n within that interval. So let's kind of visualize that. So they had a diagram in the exam. I just didn't put it here. I figured I'd draw it. It's easy enough. Okay. So we'll say here we have F1, F2, and F3. Now F1 is going to be active on so n minus 1 over n. Okay, so it would be 0, 2, and then we have n over n plus 1, so we'd have 1 on 2. I said active, I'm going to introduce that term later, but I'm not quite using it the right way. 1 on 2, n over n plus 1, so 2 over 3. And we have u acting on 2 over 3, n minus 1 over n, yeah. N over n plus 1. 3 over 4. We will place 1 here, and 1 here. And we'll say, yes, you go there, there, you go there, there, you go there, there. Bunch of little spikes. And the heights of those spikes are 1 on n. So this is 1, this is 1 on 2, and this is 1 on 3. So that's kind of what it's looking like. Now, they did also mention it is 0 elsewhere between 0 and 1. So we'll draw that in. There we go. Pretty graphs. So does that sequence converge pointwise and or uniformly on 0 to 1? So let's focus on that first. We'll look at pointwise. As I was discussing earlier, we have pointwise first, often the one you go for. Easy one to find, and then just check whether the limit you get, if it is pointwise, is itself uniform as well. This up here, just a kind of condensed way of writing it. I was going to write like the piecewise proper definition, but it just ended up being way too messy. I was going to have a line here, and then 0 elsewhere, but the equations of these lines were killer. So we've just got here a little symmetric spike with height 1 on n between this boundary and 0 elsewhere. So we'll try to find the pointwise limit. First, we're going to introduce, actually no, we're not going to introduce that yet. So, okay, we can see that our function is between 0 and 1 on n inclusive. So limps up pinching argument, yes, okay. So same kind of limiting supremum pinching argument that we used previously. It was somewhere around, I actually drew it up, did I? Maybe. It was here. So limps up, here we were. Again, pinching argument, limps up, consider carefully. Going back down here. Where are we? There we are. Whether the function f of fn may be characterized as just the 0 function. Quite nice. And we can kind of see that. You can imagine as you continue this, it gets smaller and smaller. I think, so I prepared a little graph. I'll actually show you that now. So I've made a little function here. I realized I could do it with absolute values, and I've just made a little b function here to do with the boundaries. So we could say here f of x 1, you get that. F of x 2, 3, 4, 5, 6, and so we can see that as n gets larger and larger, that should just shrink to 0. Intuitively, we can understand that, but we require the limps up sort of argument to properly communicate it and confirm that it is true beyond a doubt. So now that we've got the pointwise, we'll have a look at the uniform. It converges uniformly if we have the infinity norm approaching 0 between the 0 function and f. So just changing this around a bit, you could flip these two. You could do fn minus f, because really f, that's 0. It's not going to be anything nice. We know that this norm is symmetric, or commutes with elements. So we can just switch them around, take fn and sub in the supremum on the domain definition. We can see that the supremum of any given function is just 1 on n. That is the maximum height of its spike. And we can see that goes to 0. So the convergence is also uniform. Now we'll have a look at the series. So we'll look at the pointwise convergence of the series first. This is a case, like I say here, where the Weierstrass M test would actually fail. Reason being, we know that the supremum, and in fact the exact maximum value of every single one of these spikes is 1 on n. So that would give us that mk equals 1 on n, sorry, 1 on k. K and n I'm using interchangeably just as the indexing pronumeral. But mk, no, this should be nn, because we're using n in this situation. 1 on n, and we can see that the series from n runs 1 to infinity of 1 on n, well, that's the harmonic sequence, which diverges. So Weierstrass m-test isn't going to be able to confirm, nor can it deny the convergence here. Now, just looking at this actually, did I just use Weierstrass m-test to talk about pointwise convergence? Weierstrass m-test only applies to uniform. Yeah. So that should have been held off until we talked about the uniform convergence, but the same points still apply. Just don't really worry about that. This talks about uniform convergence. So move on. We're going to introduce a little helpful term. I mentioned the term active earlier. I'd like to say that a function, any function in the sequence, is active where you're in the non-zero portion of its spike. So we'd say here that the region in which f1 is active is this region. Here f2 is active, here f3 is active. And to be more kind of proper about it, we're saying it's this open interval here. It's going to be helpful for condensing a lot of our writing if we can just say active rather than within that interval. So where are we? We are here. So it's active. Fn is active for any t satisfying fnt does not equal 0. We'll look at the set, the largest set that Fn is active for, that is that open set. We can see that it is the spike in this region, but we know it's going to be 0 at either end of the spike, exactly here and exactly here, because it's a continuous function. It cannot be non-zero there while still remaining continuous and being a symmetric spike. So we'll say that this is the largest set that Fn is active for, non-zero. This is disjoint from the largest set that Fn plus 1 is active for, perfectly disjoint actually, it's just right next to each other. You can see that the lower bound of this is the upper bound of this, and they're both exclusive, so there's just one point in between them, that is n over n plus 1. We saw that happening back here in the diagrams. We saw, oh, 1 on 2, that lines up with 1 on 2, and oh, 2 on 3 lines up with 2 on 3, and that continues happening. So we know that no two adjacent spikes are ever simultaneously active, and that gives us that since the spikes only like move away from each other, you know, adjacent spikes are the closest you can get, no two spikes are ever both active. That gives a nice little idea. It gives the idea that, oh, well, if only one spike is active at any given time, the sum is going to turn into a very nice thing. It's just going to be your function at a value, your function of the series, is either going to be 0 if you're between spikes, or just behave like one of the spikes, because the infinite series, you can write it as this if you'd like. Right here. We're going to call the sum here from k running from 1 to infinity, fk of x is equal to, if we break this up into the infinite piecewise function, we can say that it's, of course, f1k plus, well, we'll say it's the sum. I'm just going to say sum between 0 and 1 on 2. But that sum of fk's, well, fk1, f1, sorry, f1x, is going to be active, but the rest are going to be inactive. They're all going to be 0. So we just say f1. Same story with f2. We'd get 0 plus f2x plus 0 plus dot dot dot. So it'll just be f2 for the second region. And we get f3x, 2 on 3, less than x, less than 3 on 4, dot dot dot, dot dot dot. And we get kind of beyond that. I'll just like partition this a little bit. Maybe I'll do it in a red dotted line just to represent that it's not really part of the function writing. 0 otherwise. So that is 0 in the kind of regions between. So we can condense that upper portion, the part above the red, to just fnx, where fn is active for x, and 0 otherwise. We know it's well defined since no two functions of the sequence are ever simultaneously active. We talked about that result earlier, and the otherwise portion, like we said, to cover those little gaps, countably many gaps. Okay, some 0 and none are active. All right, so that is what we are saying it converges pointwise to. And I made a little diagram here. Diagram continues. We can see here, if you add the second spike, so I've just got the partial sum here, going up to n. So the sum up to 1, sum up to 2, 3, and you can just see spikes are getting added every single time. And that continues. Okay, before we move on to uniform convergence, just check the chat. Yep, runs all right. Cool. Right, hope it's not boring everyone. Hope it's actually somewhat okay. But yes, let's look at the uniform convergence. So let's first construct a sequence of partial sums. So Sn from 1 to infinity, where Sn is the sum up to the nth spike. So we can see kind of through the logic we were talking about earlier, this same logic, just rather than the infinite sum, we only go up to the nth sum. We can see it's going to be the collection of all spikes up to and including the nth spike. So going back to this diagram, these are all spikes up to and including the third spike, sum up to 3. So going back here. This is a helpful little tidbit, just to kind of give us our intuition to think of it as just spikes, kind of, what is it, concatenated. We can then analyze kind of the sum that we were talking about earlier. Well, I called this S. It's not really a sum in its current form, but S here compared to Sn. We can note that if you take S minus Sn, then it's going to be the curve with every spike from the n plus 1th spike onwards, because, well, if you've got here curve, and let's imagine that you have S being this green curve, and it's got all of these spikes. Spikes get thinner as you go on. Okay, and that continues. They just get smaller and smaller, but imagine that's the infinite one. Then we'd say that, imagine you have here S2. That is giving, once you subtract one from the other, you get every spike from the n plus 1 spike, the third spike, onwards. And you can imagine that logic with any given integer, any given positive integer, n. So we can then see that the supremum of, well, this infinite norm, this supremum for k greater than or equal to some n of this is n plus 1, 1 on n plus 1. That's because the spikes just get shorter and shorter as you go along. And so the greatest height spike that there is going to be, the greatest peak, is going to be the first spike that there is. And since we're dealing with k greater than or equal to n, for n being a positive integer, then we are going to have the n+1th spike being the best we can do. And we can see that approaches 0, and so we get uniform convergence. And I believe that's it. Okay. So I'll stick around here just to see if anyone has any questions, but that is, I believe, our presentation. Feel free to, oh, I just realized this is still called, oh no, this is part 1. Feel free to ask any questions you'd like, or yeah, make sure you go to the Friday seminar. I do believe it's on Friday. I know that we will be going through topology and, well, really just the rest of the course. Okay. But I'll stick around maybe until 5:2, a little longer. Okay. Okay. I think we'll leave it there.